Okay, let's wait a few minutes that the participants join us. Okay, the numbers are increasing rapidly. We're already at 33, 37, 50. We should go for the record, although I don't remember what the record is, yeah? But we'll find out. Okay, the numbers are still increasing. Okay, let's wait one more minute and we can start. Okay, I think I stop sharing the slide. People know now that we are in the right. Okay. Yeah, I think we can start. So good afternoon, everyone. Welcome to the, I think it's the third mini school of NITheP. My name is Francesco Petruccione, and I'm the interim director of NITheP. And today, I'm very happy to introduce to you Amira Abbas. Amira has a very interesting career because she studied actuarial sciences and quantitative finance. And then she started working as a researcher in one of our major banks in South Africa. And then she decided to become a physicist. Yeah? And since then, she already completed her master's and is now well on the way to complete her PhD in my group at UKZN in Durban. So Amira, thank you so much for agreeing to be with us this month. Yeah, and we are really looking forward to hear how to program and do some machine learning on a quantum computer. Yeah, and with us today is also, many of you have probably already seen him, Ilya Sinaisky, and he will coordinate a little bit the questions and answer session. And please don't be shy, make use of the Q&A facility, and yeah, and Ilya will moderate it during the talk. Amira, if you would like to start sharing your screen, you're welcome to begin your presentation.
Okay, let me do that now. Okay, do you see the full screen?
Perfect. Thank you very much.
Okay, perfect. Okay, thank you so much for such a kind introduction, Francesco. I'm really happy to be here for this mini school. I think it's a really cool idea. And yeah, for those of you who don't know me, I mean, I am doing my PhD now in quantum machine learning, and I'm very excited to tell you a little bit more about that today. And I'm also sorry for starting the talk an hour late. I mixed up some time zones and had other commitments as well. But from next week onwards, I think the talks will all start at 2 p.m. Okay, so let's begin. I want to just quickly highlight some applications of quantum machine learning, right? So I don't want to spend too much time on these because the fact that you are here means you already acknowledge that quantum machine learning will be something important in the future. But some applications that I think are really cool are, for example, in the field of logistics. So in logistics, right, there are often very many variables that interact with each other. Things like transportation systems, right, where you're delivering products to different places, and so many things interact and can go wrong and affect each other. And quantum computers and quantum machine learning algorithms, for example, are really, really good at complex combinatorial problems. And I think that they can have some really interesting applications in fields like logistics. Then finance, as Francesco mentioned earlier, is actually my previous background. I studied actuarial science and worked in asset management for a little while. And I actually think that quantum computing and quantum machine learning has a lot to offer there as well. There have already been demonstrations of quadratic speedups using quantum algorithms in things like Monte Carlo methods that come up in pricing assets, in risk management, in portfolio management, and pricing derivatives. And I think that quantum machine learning actually can offer some very innovative financial modeling techniques. And I think that there's a lot to actually find out there. And Goldman Sachs, for example, have now started their own quantum machine learning and quantum computing group, where they've invested in researchers to look at how quantum computing can affect their work in asset management, which I think is quite promising and quite cool. Then material science, which of course I think arguably will have the highest impact if we can get quantum machine learning to do very interesting things in the future. And that's because the study of molecules is just really, really difficult to do with the hardware that we have today, right? And the hope is that quantum computers can handle these very difficult calculations and simulations that occur in nature with chemistry and quantum chemistry. And maybe we can see new things like new types of medicine, different drug design, more efficient modeling in this area. And I think that that's really promising. And the last thing I'll say is applications that pertain to modeling the universe. And I'm sure many of you already know this quote, and I say it all the time in talks because I think it's quite a nice one. But like Richard Feynman, I paraphrase it a little bit. He says that nature is quantum, and if we hope to model it or understand it, well, then we have to incorporate quantum mechanical effects into whatever we want to study or simulate in nature. And so quantum computers innately do this, and perhaps quantum machine learning algorithms can help us understand the universe better and answer some really cool, big and beautiful questions. So what do I mean when I say quantum machine learning? When you ask somebody in the field to define it, they very often cast it into these 4 blocks. And what you're seeing in this picture is whether you have classical or quantum data interacting with classical or quantum devices, quantum hardware. So for example, typical normal classical machine learning is in this block here, where you have classical data processed with a classical computer. But you can also have quantum data that's processed on a classical computer, right? So maybe you have some data that comes out of a quantum mechanical experiment, and you use a neural network, for example, to optimize parameters around that data. And then perhaps not so common is having quantum data that's processed on a quantum computer, but this is also a type of quantum machine learning. But the definition that I will talk about today and in the series of lectures is really this red block here, where we have classical data and we'll process it using a quantum computer. Okay, and then something else I wanted to just mention very briefly before we go into the content of today's talk is the Quantum Open Source Foundation. So I encourage you to go and visit this website. It's qosf.org. And they have a whole bunch of cool things on there, like how to start quantum computing, very nice resources, list of open source programs that you can use to program quantum computers. And just recently, they launched a mentorship program. So now, no matter what your background is, you can apply for this mentorship program, and they pair you with very interesting researchers around the world, and you can work on projects that interest you specifically on the topics in quantum computing that you find fascinating. So I think this is really quite nice. And judging from the last year's program, some very high quality output comes from these like papers and very useful things. So I encourage you to check that out. Okay, so what we'll cover today is an introduction to something called variational circuits. So for those of you who are familiar with quantum computing, you will know all about variational circuits. And then using these variational circuits, we will construct and discuss a very, very simple model. And then we'll need to understand how to optimize this model or this circuit. And then lastly, I want to show you how beautifully simple it is to build this simple model with a software framework called PennyLane. So over the next couple of weeks, we'll use PennyLane and Qiskit. Both are open source software programs, software packages to program quantum computers. But today we'll just look at PennyLane, and I'll make the code and the notebooks available to you, so you don't have to follow as I do. You can just watch today, and then you can try it out a bit later. And then something I just want to highlight is that I assume at least a basic knowledge of quantum computing in this talk. So what does that mean? Well, you should at least be familiar with circuit notation, circuit diagrams, and the objects in these circuit diagrams. How do they look? What are their mathematical representations, and how do they interact? And if you don't know this, that's fine. I encourage you then to go and watch this previous mini school by Daniel Park, which is on the NITheP YouTube website. And then you can also read like the first 3 chapters of this textbook, which is also, if you Google it, you can find it easily online. And then you should be okay. And for the purpose of today's talk, I think you'll be fine because the content is really quite high level. And then when it starts to get, I think, a little bit more sophisticated next week and the week after, then this will be quite nice to have to follow. Okay, so machine learning. Machine learning 101, right? Oh, by the way, I should say that we can make this as interactive as you want. Please feel free to ask questions at any time and stop me. So I like to think of machine learning very broadly as we always have some sort of model, let's call it F. And this model usually takes in some data and it depends on some parameters, theta. And this parameterized model, the goal of machine learning is to try and find an optimal set of parameters such that this model gives you something useful. It gives you maybe a prediction or an outcome or something that's useful in a machine learning setting, a task that you want to understand. And really, quantum machine learning is just trying to figure out, well, how can we make this quantum, and can we get an advantage if we make this quantum? Can quantum computing offer us something different that we can't necessarily have on a classical computer? So when I talk about or think about quantum models, I like to broadly divide them into 2 kind of categories. The first is just a class of deterministic quantum models. And what I mean by that is just that when you have some sort of quantum state and you do some things to this quantum state, the output that you get is something that you will get with certainty. It's something that will be like deterministic in nature. And an example of a deterministic quantum model is the De-Sieuze algorithm, which I'm sure a lot of you have heard of. Okay, but then the other class, which is increasing in popularity now in quantum machine learning and in quantum chemistry and a whole bunch of quantum computing applications, is this class of variational quantum models. And I list some of the algorithms in which variational circuits, variational quantum models are a part of. And we'll actually talk about this variational quantum classifier, not next week, but the week after. But the difference in the variational quantum setting is that what you get out of your quantum circuit or your quantum model is no longer deterministic necessarily. It's actually a probability distribution over possible outcomes. You can get like an expectation value, for example. And these circuits in particular depend on some parameters. Okay, and so quantum machine learning very much kind of relates or invests, I think you can relate it to deterministic algorithms and build those in as well, but I'm going to talk about the variational setting. And I'll present now a framework of what I mean when I say a quantum machine learning algorithm using a variational model. And so you can imagine having some qubits in your system, right? The first step in this quantum machine learning framework or template is then to apply some operations in the system. So some gates, some unitary operations, such that these operations are meaningful. So they need to kind of somehow encode your data and also depend on parameters, right? So can be a parameterized kind of model. And if you had to then write down the quantum state after you do some operations, then what happens here, what you should get here is some sort of encoding of a model function that encodes your data and that depends on some parameters. And then perhaps the one thing that's a little bit different in the quantum machine learning setting is then you need to apply a measurement to your system. And from this measurement, you need to extract an output. And there are many different ways to do this. There are many different ways to encode your data, to have your model depend on different parameters, to measure your system and to extract it. So in the series of the next couple of talks, we will delve into each of these components a little bit more. So today we will discuss the variational component in the quantum model. And I want to just highlight that why variational models have become so popular as of late. And the reason I think is largely due to the fact that they just work. They can work really well on the hardware that we have today because they're robust to noise. And so even though the qubits that we have right now are still not that many and very noisy, these variational techniques seem to be robust to noise and seem to show like quite a lot of promise. And so they've been adopted into quantum machine learning algorithms quite a lot to demonstrate that near-term hardware can do interesting things. Okay, are there any questions?
So far, no.
Okay, cool. Okay, so now we'll start with a very simple example, right? So, and if you're from a quantum background, please forgive me. It's just so that everybody is on the same page. So imagine we've just got one qubit in our system, right? And we can write this qubit in its ket vector notation, and it looks like this. And then let's say, and then because it's one qubit, we can also plot it, right? We can use the block sphere representation, and we know that a qubit in state 0 has this kind of vector representation in the block sphere. It's just like this vector pointing up. And then if we make a measurement to this qubit in the sigma z basis, so we can measure in different bases, right? We've done nothing to this qubit. But let's say we want to measure it in the sigma z basis, and we know that we can write the sigma z operator in a matrix form. And when we do a measurement, then we can think of it as kind of sandwiching these measurement operators by your quantum states, which in this case, your quantum state is just the 0 state. This is a bra vector. And if we had to write this whole thing out, what we would get is a sigma z expectation value of 1. And so this expectation value of 1 corresponds to your state being in state 0. And quite trivially, if you had to, let's say, flip the 0 state to state 1, let's say we apply an X gate, and you can go and do the actual like matrix multiplication, multiply this X gate on the 0 state, and then check the vector representation that you have afterwards, you'll be in the 1 state. And then if you were to do a measurement again in the sigma z basis, and you write that whole thing out, then you get an expectation value of -1. And so this really corresponds to the 1 state. And so the sigma z expectation values lies between +1 and -1, depending on the things that you do here. So the operations that you apply to the qubits. And so this really ties in very closely to the idea of trying to understand variational circuits, right? So in a variational setting, you have some operations that are done here, but what's done here depends on some parameters, which you can change and tweak and train. And this notation here just means that there are multiple qubits in the system. It doesn't just have to be one, but in our simple example, we'll consider just one qubit for now. Okay, so then returning to our one qubit example, let's say that the parameterized operations that we do to our qubit is an Rx gate. And so we do an X rotation by some parameters, θ1. And then we do a Y rotation by another parameter, θ2. And then we do our measurement. So we can write out actually all the mathematical representations of each of these components. We know that an X rotation can be written in terms of cosines and sines, and the angles of the rotation is this value θ1. And similarly with the RY rotation. And then if we had to just like consider the state before measurement, right, let's call it psi, then we can write it like this. We have an X rotation acting on the 0 state, a Y rotation, then applied after that. And just notice here the difference in the order of the Dirac notation and the circuit representation, right? So from the circuit, we go from left to right, and in Dirac notation, we kind of go from right to left. And then if we wanted to calculate the expectation value, the sigma z expectation value, well, then we can expand this whole thing. Remember, the bra vector is just like the complex conjugate transpose of this thing here. And I'm not going to write out the full math, but you're welcome to do it at home. But what I want to highlight is that this is a very easy example to actually do with your hand, right? So we can actually calculate the answer, and it works out to be cosine of theta 1 times cosine of theta 2. Okay, cool. So now we know that if we have a variational circuit, it depends on some parameters. And then we have some measurement output that will also depend on some parameters. But then you might ask, how do we choose the parameters now? I mean, what is the point of doing this? We can plug in anything, and why would we do this? And so choosing the parameters is really the next key thing in understanding a variational architecture. So again, if we go back to this like general picture where we've got some qubits, we do some operations that depend on parameters, we get a measurement. In quantum machine learning, what we want to then do is we want to take this measurement and interpret it as a label or an output class, because in classical machine learning or in machine learning in general, we need labels, we need outputs in supervised learning settings. And then we can take this label and we can plug it into something called a cost function. And a cost function, you can think of it as a way to assess the performance of your model. So let's say that we get a prediction here that we interpret it as a probability of being in a certain class, let's say class 1 or class 0. And we take this prediction for, we choose a random set of thetas, we take our prediction, we put it into our cost function, and our cost function will say, was our prediction correct or was it not? And then it measures this discrepancy. And then you can then figure out how to minimize this cost function. So this cost function increases with the more you get wrong. And so you want to decrease it as much as possible. You want to minimize the cost functions so that you can get better results and better predictions from your model. So your function gives you information on your performance with your particular parameter set. So it's also a nice way to measure and how to choose your parameters accordingly. So then the next step is you see your cost function, you figure out how to update your parameters, and you repeat this process such that your cost function is minimized. And so this is really the variational architecture that is employed in a majority of quantum machine learning algorithms. And if you liken this to classical machine learning, the frameworks are very, very similar, right? So maybe with just the addition of data here. So you have some parameterized function, then you apply some post-processing function like nonlinearity. In the case of neural networks, this can be you interpret this outcome as a label, you plug this into a cost function, and then you figure out how to update your parameters. But in a classical setting, this is very clearly defined, this step, right? How to figure out how to update your parameters. So if you have neural networks, for example, things like backpropagation and calculating gradients are very easy to do. But we'll discuss a little bit later how we can do this in a quantum setting. Okay, so the next step then for us is to define a cost function that we want to minimize, right? So we spoke about our very simple 1-qubit circuit that depends on some parameters. And then now using the output of that circuit, we need to define some objective function, some cost function that we do want to minimize. I see a question, yeah.
How can it be applied to reinforcement learning? And can it be applied for reinforcement learning?
Yes, yes, definitely. I think actually a lot of people that do quantum machine learning, quantum reinforcement learning, just use this variational architecture. There are a lot of papers that have proposals for quantum reinforcement learning algorithms, and they are essentially a variational framework. So when we discuss the variational quantum classifier, not next week, but the week after, then I will relate to reinforcement learning because I think the two are very closely related. Okay, but
thank you.
Yeah, okay, cool. Sure. Okay, cool. Next is defining our cost function. Right, so remember I said that we want to have some sort of goal to get to. And as a user, as a machine learning engineer or a quantum machine learning engineer, you have a choice of what cost function you want to use, right? You can define it. So common ones in classical machine learning are like the mean square error. It's like the squared error between your prediction that your model gives you and the actual true prediction. But let's say in this very simple example, we just define the cost function to be the output of the circuit. And we know what the output of the circuit is because we're doing a measurement in the sigma z basis. And this is a very, very easy example, right? So we can actually write in this case what the output of the circuit is. But let's just assume naively that this is our cost function. This is the thing we want to minimize. So we want to pick a set of thetas, theta 1, theta 2, that minimizes this output. And I mean, just looking at it, it's very obvious what those values are, right? But let's just say, I mean, in higher dimensional spaces with more qubits, this is not so trivial. And I just want to point out that, like, we already know that if we are in the 0 state, we get the maximum that can come out of this function because this thing is bounded between 1 and -1, right? And if we're in the 1 state, then we get the minimum of this cost function that we defined. And so really what we're trying to do is we're trying to pick a set of parameters that takes our input state, that maps our input state, which in this case is the 0 state, to a target output state, which in this case we want to get to the 1 state, right? Because that gives us the minimum value of the output of our circuit, which is the cost function.
Sorry, Amira.
But
Can I ask you another question, which I think
yes.
is more relevant for understanding that, okay, how do you get to your target variable? And I think the person who's asking is talking about theta 1 and theta 2.
Mm-hmm. Yes, exactly. So there is the question, how do we pick these optimal thetas?
It's not specified, but I think maybe, just where they're coming from.
Okay.
Because I think it's on the level of misunderstanding of the circuit.
Okay, no problem. Okay, so they're just kind of like dummy variables, which you can think of. So if we go back to our original just depiction of the example, we said, let's just say we have a model where we define the operations that happen. So in this case, we defined an operation that consists of an X rotation. And this X rotation happens, we rotate the qubit along the x-axis at an angle equal to a parameter. And we just call this parameter theta 1. And then we do another rotation in a different axis, y-axis, and we rotate by an angle of theta 2. We just call this parameter theta 2. So these are just defined parameters, and I haven't really specified what they are as yet. But there's something that we want to tweak and train and optimize such that the output of our circuit can be useful to us as a machine learning model, for example, a very basic one. So that's where the thetas come from in these, and if we write out these actual rotations in matrix form, then this is what they look like. And if we do this full multiplication here, then we get this output that depends on our rotation values.
Is the number of parameters is arbitrary to choose?
Yes, so it can be, right? So you can then apply 5 different rotations that depend on 5 different parameters. So just like the number of weights in a neural network is arbitrary to choose, you can define how many neurons you have in hidden layers, how many hidden layers you have. The architecture is really for you as an engineer to decide. The same thing goes in this variational setting for quantum machine learning. The architecture is up to you to decide, and it really depends on your problem.
Okay, thank you.
Cool. Where was I? I think I was here. Yes, I was here. Okay, so yes, so we said that we want to, in this very naive, simple setting, we want to be able to pick some parameters that kind of navigate or map our input state to some target state. And in this case, the target state needs to correspond to minimizing our cost function. Okay, so we need some sort of optimization of this cost function, right? And in this setting, it's really easy to understand this because we can write it all down. We can write down the analytical result. But in a lot of cases, it's not so trivial. So we'll continue with this, and then in the next lecture, or the lecture after the next one, we'll see that writing these solutions down are not so easy anymore. So how can we do optimization of a cost function? And I mean, like I said here, it's easy, but if, let's say, we had a very, very complicated one. And in classical machine learning, what is normally done is we use gradient-based techniques to do cost function optimization. And I'll explain in a very high level what a gradient-based technique consists of, but there are many different types. And I think the most popular one is something called gradient descent. And what gradient descent does and it's also very well established across a host of classical machine learning models like neural networks and so on. But let's imagine that you have your cost function, right? And your cost function, generally it's very high dimensional and difficult to plot, but let's say we've got a very easy one and we can actually plot the cost function. And we plot it in terms of different parameter sets. So on the y-axis is the value of your cost, which you want to minimize, for each possible set of parameters, theta. Okay, so each possible combination of parameters you can have in your model is on the x-axis. And so this is the thing you want to minimize. So gradient descent says, let's just pick an arbitrary set of parameters. Let's say we pick this set here. This will correspond to a cost function equal to, I don't know, let's say 0.3 or something. Then with the gradient descent algorithm, it calculates the derivative of this cost function with respect to parameters at this point. So you get a gradient vector, and then you descend down in the opposite direction of this gradient vector, which is why it's called gradient descent, right? So it tells you that you need to update your parameters in this direction to lower your cost function. And so you keep doing this, moving down this cost function, descending down the gradient, until you eventually converge to a minimum. So you get a parameter set that converges to a minimum cost value. And if you're already familiar with this in classical machine learning, you might then immediately ask, well, how on earth do we calculate gradients in a quantum circuit, right? Because it's pretty well established how to do this classically. You have backpropagation and so on for neural networks and other techniques. But for a quantum circuit, this is a little bit not so easy, right? I mean, especially when you have more qubits in your system, how do you do this? And thanks to a very nice result from this paper here, it actually shows that if you have some sort of circuit that you want to calculate the gradient from, you can do that by just simply shifting the parameters in your circuit. So this original circuit depends on some parameters theta. If you shift those parameters up by a small amount, calculate the output, and you do the same thing, shift those parameters down by a small amount, calculate the output, and you take the difference of those two things, you can calculate the gradient. And this is really quite nice and really cool, because now we can start using things like gradient descent to optimize cost functions that incorporate variational circuits. And so there are lots of software frameworks that actually already have these gradient descent optimizers and very cool optimizers already pre-built in them. I will be talking about two in particular over the next couple of weeks. Qiskit is one of them that was developed by IBM. The other is called PennyLane, which is for machine learning specifically, quantum machine learning, that was developed by a company in Toronto called Xanadu. But there are others, right? I mean, there are other companies that have quantum computers as well. Rigetti is one of them, and Forest is also a Python package that you can use. Microsoft has Q#, and if you go to the QOSF website, you can check out a nice list, exhaustive list of open source quantum frameworks and softwares that you can use, software packages. Okay, I see a lot of questions popping up. Maybe now's a good time to take some.
Okay, yeah. I mean, let me just, okay, there is a question still on the parameters, and that's probably related to the hardware implementations. Could these parameters, theta, be related to the microwave pulses for qubit rotations?
Yeah, I have no idea. Ilya, you probably can answer that.
No, but I mean, in that case, I mean, what Amira have demonstrated to us is called quantum circuit. It's a high-level implementation of the quantum algorithm. Would it be microwave pulses? Would it be rotations of the controlled beam splitters in the linear optical settings for the quantum computer from the Xanadu implementation, or would it be some sort of Sorensen-Molnar gates, which are related from the ion qubits, which are made by company IonQ? It will depend on the hardware implementation. In the Qiskit and in case of superconducting qubits, of course, splitters are controlled by the length of the microwave pulses. That's clear. Thank you. Okay, now there is a little bit of confusion about the cost functions. Let me just shot at you a few questions on the cost functions. Okay, what is the physical significance of minimization of cost function?
So the physical significance, or the reason why we do this, is to give us some sort of performance metric of our algorithm, right? So we want our machine learning model to give us some predictions, and we want these predictions to be correct. We want them to be useful. We want them to do things that make sense. And so the cost function really, it measures how well your predictions are doing. So if the cost is very high, your model is not very good. The predictions it's giving is not robust. And so minimizing the cost function then means like you're choosing the parameters so that you're making your model better and better each time. And when you get to the absolute minimum, then you, in theory, your model should be using the parameters that will give it the best results for your specific machine learning task.
Okay, so is it preferable to choose a cost function which possesses a global minima?
Which what, sorry?
Which possesses a global minima.
Yes, definitely. Given... yes, but this is actually quite difficult to tell a priori. So I think how cost functions and their landscapes look is a very difficult thing when you get into very complicated types of models. So there are different ways to try and understand the loss landscapes of various machine learning models, right? And I think in the quantum space, this gets even more difficult to do because people don't really know how to quantify it and what it really means. So choosing one with a global minimum would be great because we know that there's an absolute low value, but yeah, I think it's very difficult to kind of understand the landscape in general.
Okay, but if the minimum is not global minimum, maybe it's just a local minimum, we won't be able to get the lowest values, is it right?
No, you can still hit a zero cost value in the local minimum. And it's actually really bad, right? But then and this generally happens on your training data. But then you should then start to do things like trying to understand how well your model generalizes by testing it on test data. And then from there, you can easily start to see the model, even though you've trained it to a zero cost function, zero cost value on your training data, it doesn't correctly predict outcomes on new data that it hasn't seen before. So it doesn't really generalize very well. And so then you can start to think, you can start to like realize that actually your cost function minimization got stuck in a local minima. And yeah, and so this is not really good, I think. These are really good questions. Yeah.
Okay, and is it possible to avoid the local minima using the gradient descent?
Yeah, I think the reason why gradient descent is so popular is because exactly this argument. It's fast. It's very fast at converging, and it jumps about randomly. So it should, in theory, avoid local minima easier than some other methods. But this is also really dependent on certain hyperparameters you choose, right? So with stochastic gradient descent, you can adjust things like your learning rate, you can adjust your momentum, and these all affect your convergence speeds and your convergence success. So you can still get stuck in local minima. It's just something that is really hard to avoid, and it comes, I think, with experience, and different examples have different benefits, and different optimizers work better under different circumstances. So I think this is a really difficult question, but it has shown some promise against avoiding these problems. Yeah.
Okay, so, and maybe we can take a couple of more questions because there is quite a lot of questions and we'll probably need to move on. Let's take a couple of more generic questions, and afterwards probably you can go to the demonstration. Do you think the variational machine learning will be useful in the data science/big data?
Yes, I do think so. Once we can have computers that can handle big data. So I see variational models as a different type of class of neural networks, for example. So there are different definitions of quantum neural networks, and we'll get to that, not next lecture, but the one after. But one such definition just very heavily depends on variational circuits. And I think that this type of model offers a lot of promise. It's very interesting. It shows, in my research, it shows very promising properties. And I think it will very much be a key feature in big data, in data science going forward, once we have the hardware to handle it.
Okay, and maybe let's take one more question, which is related to probably things which you are going to do now. Can you talk a little bit more about the encoding step? Basically encoding the classical data, say a state of space of a game in the quantum setting.
Yes, absolutely. So the whole lecture next week will be dedicated to encoding data into a quantum circuit. So there are many different ways to do this, and I particularly avoided it today because I wanted to address it properly in a nice session next week. But there are different techniques, and I think in short, we still don't really know which technique is the best. We'll go through a couple next week, but you can do things like, for example, if you have a data point with 3 feature values, you can take a qubit and rotate it about different axes by angles that are equal to your data values. So this is one idea. It's called angle encoding. There are other ways to encode information. If you represent it in a binary bit string, and this is pretty straightforward, then you can encode your data into basis states, right? So possible combinations of zeros and ones that you can represent with qubits. So I think let's leave that for next week, especially relating it to reinforcement learning. Haven't really given that a lot of thought, but thank you for bringing it up. I will, and then I'll try and mention it in more detail next week.
Okay, can I just ask one last question related to a little bit of skeptical view, because I just think it's important.
Yeah, sure.
Kind of, why we need quantum machine learning? Any use case?
Yeah, so very good question, and very important question, right? Because I think that we actually haven't tangibly demonstrated any kind of benefit right now. There are, and let me answer it in my view. Why we need it, or why we need to look at it, is because I strongly believe that quantum computers will get bigger and better. And so the next step is to try and understand if we can use them in a machine learning setting. And these computers offer inherently different methods for computation, right? And if anything, they have to at least be able to keep up with classical machine learning, but also maybe offer something different because they have quantum mechanical properties that we can harness for computation. So the goal of quantum machine learning, and for researchers like myself, is to try and understand what benefit can we get from this. And there have been a lot of promising algorithms proposed, quantum machine learning algorithms. If you're interested, check out, you can Google quantum algorithm 2, and there's summaries of lots of different algorithms there and what they aim to do. And a lot of these algorithms propose or conjecture exponential speedups or training speeds or benefits in certain settings. So there are a lot of promising things, but you're right. I mean, actually showing that we should switch over today, this has definitely not been done. So it is something for the future. Okay,
great. I think we should keep going, yeah. And if the time permits, we'll go back to more questions which are here in the Q&A.
Okay, cool, sure. I think the next thing was to jump actually into the code. So let's do that. Okay, how do I close this? Okay, do you see the Jupyter notebook?
No, we see your screen, which is saying jump to the code.
Okay.
Just unshare the screen and reshare it again.
Okay, cool. Let me do that. stop share. Okay, and should be working now.
Yep, now we can view the notebook.
Okay, perfect, cool. So what I want to show you guys, and I see we have 15 minutes left, that's actually perfect, is how beautifully easy it is to code up a model in PennyLane. So here is the full tutorial that does exactly this simple 1-qubit variational model that we discussed today. And I'll just take you through it like line by line. But really, I mean, it's just a few lines that we can do together. And I encourage you then to go and build your own kind of models and circuits and optimize them, use different cost functions and play around with everything and see how cool and how simple it can actually be thanks to software packages like PennyLane. And especially if you're familiar with Python, this will be a walk in the park. So the first step, of course, is to import PennyLane. So I'm going to do that. PennyLane. By the way, Ilya, if you see me making any spelling errors, please let me know. And I'm going to call it QML, because this is just the convention, quantum machine learning. And then something very important to remember when you use PennyLane in particular is if you're working with NumPy, you need to actually import NumPy from PennyLane, because they do a little bit of revamping of NumPy such that it can handle quantum objects and quantum circuits. So we need to actually go from PennyLane, import NumPy as NP. Okay, so then once we have our imports, the next step is to create a quantum device. And what's really cool about PennyLane is that they build in devices that you can use, quantum devices that you can make use of. So they have already inbuilt simulators. So I'm just going to show you some here. So they've got like, for example, this one that's written using TensorFlow. They've got some other simulators. So these are not actual quantum computers that you run your circuits on. They're simulators. But then they also have plugins for you to use quantum hardware and also to convert other quantum code into their code. So if you are familiar with other quantum software frameworks, you can use plugins to convert them, and it's just a really nice language. That's very high level and allows you to do a lot of stuff on the back end. So you can actually like plug in IBM's quantum computer as a device, for example, and run your experiments on the cloud on a quantum computer. So I'm just going to use, I'm just going to create a device and use a simulator. So do qml.device to instantiate a device. Here you would specify which device you use. So I'm just going to use the default qubit simulator. And then you need to specify how many qubits you want in your model, in your circuit. So in our example, we just have one, right? So we're just going to use 1 qubit circuit. And now the next step, now that we've specified that we want a quantum device with just 1 qubit, the next step is to actually go about and define our circuit, right? So let's call it circuit. And what is this circuit going to take in? It's going to take in some parameters. Let's call them params for now. And then what was the first thing we did? Well, we did an X rotation, right? About some parameter θ1, or we called it θ1. So I'm just going to say we're going to do, so again, we do QML because we're calling PennyLane dot Rx because we're doing an X rotation. And what is the value of this X rotation? Well, I'm just going to say it's our first parameter. Okay, I'm not going to say exactly what that is. And this Rx rotation is applied to the first qubit in the system. So qubit 0. There is only 1 qubit in the system. And then similarly, we do an Rx gate, an Ry gate. But this time, we'll do it with respect to the second parameter in params, right, in this argument. And we'll also apply it to the first qubit. Okay, so we've got now a circuit defined that takes in some parameters. It can be a list of parameters. Then we apply an X rotation about a value that's equal to the first value in this list of parameters. And then we do a Y rotation that's equal to the second value in this list of parameters. And both of these are applied to the first qubit. And then we want to return an expectation value, right? So we want to return QML.expected value. What expected value do we want? We want the sigma z expectation value. We can get different ones from PennyLane. That's called Pauli Z. So you can see there are different ones that you can measure. And we want this for the first qubit, qubit 0. But now also very importantly for PennyLane is you have to tell it that this function, this circuit function here is a quantum object. So you have to wrap it into something called a Q node, a quantum object. And so you can very easily do that by just using this decorator, this @ sign, and say that you're wrapping this thing, QML, as a Q node, and it takes the quantum device that you specified. And so now we should run this. And now we have our quantum circuit defined, and it's wrapped as a Q node, which tells PennyLane that it's a quantum object. And now we can start to use it, right? So we can check that our quantum circuit actually does what we think it should do. So let's say that we want to test what the circuit value would be, and we specify some parameters as say 0 and 0.5, for example. And now if we run that, then our expectation value, our sigma z expectation value is 0.8775, which is really cool. If we do 0, 0, for example, then we just get a sigma z expectation of 1, which corresponds to our 0 state, right? So this is right. It's doing what we think it should do. Okay, and then the next step is to define a cost function, and we can define anything here, right? But I'm just going to define, excuse me, very simply a cost function that just returns the circuit as we discussed. Return circuit, and x is just like some parameter, some dummy parameter. And then we can define some initial parameters, let's say, and we'll define it as a numpy array. Let's say 0.11 and 0.5, for example. Now let's check that our cost function actually does what it's supposed to. So we can say cost, and we want to pass it the initial parameters. And it does. It returns the circuit with these parameter values. So that's awesome. Really, really simple. So we've already now defined our model. We've defined our cost function. The next step is to optimize this cost function, right? Is to find the set of parameters, so the list of params in this case, that give us the lowest cost value. So at the moment, using these initial parameters, this is our cost value. And this is not the lowest, right? We need to optimize the parameters. So in PennyLane, we can create an optimizer. So let's call it opt. And again, we call on PennyLane, and we already have the gradient descent optimizer built in. So we can specify that we want to calculate the gradients with respect to our cost function using this gradient descent optimizer, which is really cool. And all you have to do is just specify something called the step size. And the step size is something called the learning rate. In other words, how big you want to move or adjust your parameters every time you do an optimization step. So every time you move in that iteration and you move your parameters to the optimal one, hopefully that minimizes the cost function, you take certain step sizes. And so you can specify how big you want to move in this sense. So I'm just going to say we'll take a step size of 0.4. And in the optimization, how many steps do we want to actually take? Let's just say 100. We probably don't need that many. And then we can set some initial parameter values. So I'm just going to say actually it's the same as what we had here, these initial parameters. Okay, so now my optimizer is initialized, and we have our model, we have our cost function. Now we can actually go about and run the optimization. Okay, so how do we do it? We can say for I in the range of steps. So we create a loop equal to 100, right? There's going to be 100 steps. Then we want to update our parameters every step. So this is also really nice in PennyLane, because you can just take your optimizer, we defined it as opt, and you can use a step, opt.step, to say at every step, update, based on my cost function, update my parameters. And then what I do here is I'm just saying at every step, at every 5 steps, then print the cost function and print the parameters, and at the end show us what the optimal parameters are. So let's run this. And it's super fast. And we can see that the cost after just five training iterations is already negative, right? So initially our cost was 0.87. After 5 steps, it goes down to negative 0.41. And then we eventually converge to a minimum, right? It keeps going down and then it hits -1. And our optimal angles, so our optimal parameters, is basically 0 and basically pi. And this makes perfect sense, right? Because we have an X rotation, we do nothing there. Then we've got a Y rotation, we rotate by pi. And then we get a sigma Z expectation value of -1, which is exactly what we want. And yeah, and then this is as simple as it can be. And then of course, you know, you can start to define more complicated circuits here, more complicated models, and you can start playing around with different cost functions. And I want to just show you lastly that PennyLane also has this quantum machine learning, how do I say, a whole bunch of tutorials and things like that on here. So I took this one from this website, and there are more advanced ones. So I think there is even something here on quantum reinforcement learning, understanding how to get data in, barren plateaus, things that we'll discuss in the next couple of lectures. So this is really quite an awesome website to check out. Okay, and then with that, I think we have like 3 minutes left for some discussion. And yes, thank you. Oh wait, I have one more slide. Okay, but I don't have to put it up in case you can't see it. The last slide just says that in the next lecture, we'll talk about encoding data into quantum states. And then in the one after that, we'll talk a little bit more about more sophisticated models. So we'll discuss like a variational quantum classifier and what it means to have a quantum neural network. And then in the very last lecture, I'd like to discuss something I find very fascinating, and hopefully you will too, is the concept of barren plateaus, which is like this vanishing gradient problems. What happens when you can't train cost functions because the gradients are no longer meaningful. Okay, well, thank you for listening.
Yeah, Amira, thank you so much for the very exciting introduction to very practically oriented quantum machine learning. Ilya, are there more questions for Amira?
Oh, there are much more. I don't think that we have a chance to take them all. So can I just read a couple and we can decide what we do with the next questions? Okay. So we use the gradient descent technique. So we use the gradient descent technique because practical implementation, we are unable to find analytically minimum of the cost function. Otherwise, one could directly set the parameter theta equal to the minimum. Is that right?
Yes, 100% correct. Yeah. So
okay.
Yeah.
Mm-hmm.
No, I think in the interest of time, let's move on. But that is totally correct, right? I put up a very easy example where we could easily write down what the minimum is. But gradient descent is for the much harder problems where we cannot necessarily write down.
Okay. Some other participants is very curious, will this Jupyter notebook will be available?
Yes, sure.
And I should answer yes.
Yes, Francesco,
Okay.
I think we can put it on the NITheP website, yes?
Definitely, we'll do it as soon as possible. Yeah.
Okay, so we probably have a couple of more minutes for a couple of more quick questions. Yes, this question is related to the choice of the number of parameters, rotation gates, and so on. So will not the increase in parameters arbitrarily increase the complexity of the problem? Is there where optimizations come in?
Sorry, what was the last part you said?
Is this where optimization comes in?
Okay, so absolutely. So increasing the number of parameters does increase the complexity of your model, but so do other things, right? So increasing the number of qubits then increases the space at which you're looking at, right? The Hilbert space. So it's one of the ways, and there are other ways, right? So also like certain types of operations also add to statistical complexity. I assume you mean statistical complexity. If you mean computational complexity, then yes, it is mostly just the number of parameters that are added in. And optimization comes in when the problem just becomes too complicated to handle, I think.
Okay. And I think the last question, what is significance of using the expectation value as the cost function? Are there other cost functions for use for quantum machine learning?
This is a very nice question. Yes, there are a lot of other cost functions, and it's exactly something that I will discuss in probably next week's talk or the week after, but definitely something that I will address in when we do the variational quantum classifier model. But in short, there are different types of measurements you can do, different types of measurement strategies. And then after you do your measurements, you can do some post-processing, meaning you can apply some classical functions to the measurement outcomes, which then you eventually try to extract a label from these measurements. So really, there's a lot of decisions that go into this as an engineer trying to build an algorithm. And you're right, there are different types of cost functions, and some of them, interestingly enough, cause you to fall into certain traps like barren plateaus, which we'll get to in the last lecture. So this is something I think is very cool, and something we'll discuss quite heavily in the next couple of lectures.
Okay.
There are plenty of questions, but I think, yes.
Should I, maybe I just also add that people can email me or, just tweet me or LinkedIn, and we can get in touch.
And what we will do, we will save all the questions in the Q&A facility, and we will share them with Amira, and we will make a plan that over the next 3 weeks, we will answer all of them. Yeah? Amira, before I thank you, I just wanted to share another piece of information with our participants. Several of them asked over the last few days whether we could issue certificates of participation for these mini schools, and we will be very happy to do so. But just to make it not too easy and to make sure that people are really paying attention, maybe after the next lecture and after the last lecture, we will publish a kind of a quiz, kind of a simple comprehension quiz. And if you answer most questions correctly, we will then issue the certificate of participation. I think that's a fair deal. So Amira, thank you very much for the nice introduction. I'm really looking forward to the next lectures. And I hope that all participants will be back with us next week. And next week we will start at the traditional time of 2 o'clock in the afternoon. So next Tuesday at 2 o'clock we will be back here, and you will be able to use the same registration for the whole course. Yeah. So Amira, again, thank you very much. Ilya, thank you for moderating the questions, and thank you to the participants for being with us and for sharing this interest in quantum machine learning. So thank you very much, everyone. We're looking forward to see you soon again. Amira, again, lots of thank yous. Yeah, thank you. Bye-bye.
Bye-bye.